introduce our next speaker, Richard Overill from King's College, using Bayesian networks to quantify digital forensic evidence and hypotheses. It sounds like the subject of this conference, basically.
Thank you very much indeed. Well, first of all, big thanks to Norman and all the organising committee for inviting me. And secondly, I want to confess great trepidation in speaking to an audience of the distinction of the people here, because I'm only a physicist who got into computer science by accident and then got into digital forensics by accident. So I'm not sure how well qualified I am to talk to you, and a lot of what I'm going to say will seem extremely elementary in comparison with much of the very, well, to me, complex and beautiful stuff that's been presented in this workshop so far. So I hope you'll be lenient with me, at least in the point of view of the apparent simplicity of what I've got to say. First of all, perhaps a kind of introduction, because I think probably I'm the only person speaking, or possibly the only person here who's dealing with forensics of a non-physical kind, or at least a digital kind, shall we say. And there are a few attributes of such forensic artifacts which distinguish them from the conventional forensics, or what some of my colleagues call the blood and guts forensics artifacts, and the way that we have to treat them and the way that we have to think about them. So I might spend a few moments just doing that, just in case you haven't already come across digital forensics. It is a very young subject, another reason why we're nowhere near as far advanced as the conventional forensic scientist, I think. Most people date digital forensics to somewhere around 1986 to 1988 as its inception, when a guy at Lawrence Berkeley Labs in California discovered a hacker in his computer and traced him eventually all the way back to a guy called Marcus Hesse in Germany. This was Cliff Stoll, who was actually an astronomer or a computer support for the astronomy group at Lawrence Berkeley Labs. And a couple of years later, when Robert Tappan Morris released the Internet Worm as a master's student, then Eugene Spafford at Purdue University traced and back the worm and to its origin and to its originator eventually. So these could probably be described 1986 to 1987, 88, as the kind of inception in a very informal way of digital forensics. Now, if you compare that to Lockhart in 1905 and thereafter, you can see that you have something like a 100-year start, not quite, an 80-year start on the digital forensics people who are struggling to catch up. And we're not helped very much by the fact that the digital electronic revolution is going on at such an exponential rate. The variety of devices increases at a fantastic rate each year. As you know, Apple brings out a new iPhone roughly every year, and all the Samsung Galaxies and all the other phones and all the different other kinds of device which are digital and hence are part of our repertoire, or are supposed to be, are coming out, and the amount of data that they hold, the volumes of data which they contain and in principle have to be analysed, is also going exponentially enormously because, of course, of Moore's law for data, or for memory as opposed to for processors. It's not called Moore's law for memory, but I've forgotten the name of the bloke that it is called after. But anyway, so we've got an explosion of varieties of devices, all of which are different, and some of which are, or many of which are now encrypted, as you all know from the recent American case of the iPhone, and the volume of the data is growing exponentially too. So we have some really big problems. And the type of the evidence that we're trying to recover, to search for, to recover, to analyse and to evaluate is also somewhat different. It's digital evidence, of course, and it's often, I suppose I should take one step back here and talk about the way that the terminology has changed. We used to talk in the 1980s and early 90s about computer crime, and then about cyber crime when it started to involve the internet, or at least the World Wide Web, and then we started to talk about e-crime and digital crime, and I suppose that each of these are supersets of the preceding one, and now with digital crime we're basically addressing crime or the evidence related to crime which involves any device which can be considered digital. And that includes, of course, things that we don't, as well as the small things that we carry with us all the time, the mobile phones, the sat navs that sit in our vehicles, and such like things, the games controllers that we or our children have at home, as well as our computers, our laptops, our tablets, and so on. It also includes the things somewhat hidden from us in the critical infrastructure. It includes the things which are around in all kinds of the utility plants, in purifying water, in controlling the flow of electricity and gas and all the other things, in transport control. Everything, in fact, which the critical infrastructure which makes for a kind of civilization or civilized society to run. And we're expected to know all about these things and try and help when things go wrong. So crimes we've seen going from computer crime to cyber crime to e-crime to digital crime. Each time the boundaries have increased, yes, so I'm giving you a sob story to begin with to tell you how difficult it all is, to try and set some kind of context. Another interesting so the kind of, artifacts then we're looking for are obviously files of data that may or may not reside in a particular place, or the evidence that a file of data of some kind has been moved from one place to another in transit, so it's communications as well as storage of data. And of course the cloud is part of all of that these days as well. And we're also looking for what we call metadata, which is the data attached to the files. When was this file created? When was it last accessed? When was it last modified? When was it last copied? And so on, because all of this is relevant. The pure existence of something is on its own is not of much use to us until we know something about timelines of its creation and possible modification, last access, and so on and so forth. The big issue that we've been having since people started to try and do forensics in a somewhat, first a haphazard sort of way, a kind of craft-like way, and then perhaps since the turn of the millennium in a slightly more systematic way, but still nothing like, I think, as systematically as the conventional forensics community, from what I can see from where my perspective, is that we haven't really got a handle on quantifying what we do. And this is a concern for a couple of reasons. First of all, because we don't have that kind of background of history and of not case law, but case studies that you have in your glass and in your DNA and in your fingerprints and all the other things that you work with. And because, again, our devices that we get are evolving so quickly that something that we learned about an iPhone 4 doesn't work for an iPhone 5 and will never work for an iPhone 6, let alone an iPhone 7, and so on. So we're having to relearn stuff over and over again, year by year, which is hard work, but it's work at least, keeps a lot of people in business. But we haven't found ways to, very well at least, to quantify the kind of conclusions that we reach when we come to the evaluation stage. We can pretty well recover some evidence. We may or may not be able to analyse it if it's encrypted, like some layers of the iPhone are. Then we may get stuck at that point, and we may have to look for other kinds of data instead. We may want to we want to, having analysed it if we can, we want to evaluate what its value is to us, and that's where the quantification comes in. And although I have a great sympathy with a guy called Fred Cohen, who was originally at Sandia National Labs and is now CEO of Fred Cohen Associates, I think, in California. But he's originally an electrical and electronics engineer, and essentially, a bit like myself, believes that if you're going to do science, you should be able to do it rigorously, not only with rigorous methodology, but you should be able to quantify what you do, and you should be able to put uncertainties and error bars and stuff on the result which you get out. Otherwise, it isn't really science. So Fred has got his kind of campaign going over on the west coast of America, and I suppose I've just, in a more gentle way, got to feeling that in about 2008, when I happened to visit the University of Hong Kong, almost by chance, and found a group there doing, called the Computer Forensics Research Group, that they had just at that very year started to think about using Bayesian networks. And so this is where it starts to, I hope, tie up for you. Now, I've got to find my down button. Ooh. Yes. So, the abstract's big enough, but you can see that what's interesting about Hong Kong, I've discovered over the time I've been working with them since 2008, is that there, to some extent the courts, not necessarily the judges and the magistrates, but the legal officials and the law enforcement officers and the forensic investigators in the digital forensics area, there's a wish for some quantitative indications of a couple of things to do with digital forensic evidence and the evaluation of that evidence in terms of hypotheses or narratives. And one is that they would like to know something about the probative value or the probative weight of a particular piece of evidence, an item of digital forensic evidence to a particular case. They want to know how important a particular piece of evidence is, and if it's not there, is it going to cause the case to fall apart, crash completely? And the second thing they're interested in is getting the relative plausibility is a phrase or word I like to use, but the of competing stories, hypotheses, narratives about how the digital evidence that has been recovered and analysed came to be there. In other words, if you like, the explanation that the prosecution might wish to put forward to the court versus, in an adversarial system, the explanation that the defence might like to raise as to say that the same evidence, not contested, has a perfectly innocent explanation. And they would like to get some idea of the relative weights of these two kinds of these two explanations. And the reason I think that they want this is not so much to drag it straight into court and say, my lord, the prosecution's explanation has a 90%, let's say, a plausibility rating compared to only a 10% for the defence or anything like that. But they want to do this, first of all, to aid their digital investigation, the forensic process itself, and secondly, they want to do it to aid the decision of the prosecutorial authorities as to whether there is a likely prospect of a successful conviction. In other words, not going forward, as it were, blindly to hire silks and counsel and so on, when there isn't what we would nowadays, I guess, in the UK at least, call a reasonable prospect of a successful conviction, or something similar. So the Hong Kong group were just putting their feet in the water in 2008 when I first visited them with Bayesian Networks, and since then they've produced a number of them. And the reason that they've worked in this way is that they've discovered, or they haven't discovered, it's known from the law enforcement officers in Hong Kong Police and Hong Kong Customs and Excise and other such departments that about 80% of the digital crimes that take place in Hong Kong in any sort of period, any year or whatever, for about 80% of them can be accounted for by about 5 or 6 template crimes. In other words, to say there's an awful lot of copycat digital crimes going on, and if you understand one of them, then you understand all of that lot, because they're basically script kiddies or people doing similar things. And if you can find a template way to express and understand one of those template crimes, you've basically got all of them kind of under your belt. There's very little variation between them. So their idea was to try and find Bayesian networks to analyse each of these 5 or 6 frequently occurring digital crimes in the Hong Kong Special Administrative Region in a way of trying to concentrate their efforts and to focus their investigatorial efforts as efficiently as possible. So when I joined them, this is what they were just starting to do. So I've got to acknowledge immediately work carried out in collaboration with Computer Forensics Research Group at University of Hong Kong, headed by KP Chow, the Hong Kong Police Force Cybersecurity and Technology Crime Bureau, headed up by Frank Y.W. Law, and the Hong Kong Customs and Excise Department's Intellectual Property Rights Protection Team, headed up by Michael Kwan. So those are people without which. So I hope I've given you a little bit of a background, first of all, to where I've come from. So on the relative plausibility, as they like to call it, well, good old likelihood ratio, we've heard a lot about that already, and I'm sure this isn't the last. This is what they like to use in terms of this. Of course, we know that there are a lot of things that can be said against likelihood ratio and misinterpretations of it, so we need to be careful. And they try to find, in the cases where they do a likelihood ratio, they want to find the hypothesis, the narrative, if you like, that the prosecution believes happened in a particular case, and then find out what is the commonest defence against this by the defence case. And assuming that these two together do cover the hypothesis space, that there are no third or fourth possible alternatives, then of course we have the ratio, likelihood ratio over on the right. And the approach taken was then to design and build and run Bayesian networks for the prosecution and for the defence case. So this was for them done in one particular case that I thought I'd just show you. It's not the only one, but it's one that they were quite successful with, I believe. In Hong Kong, there's one of their big 6 crimes, digital crimes, is online auction fraud. People misrepresenting the item to be auctioned, and as it were, in some sense, replacing the genuine article with a fake counterfeit article, but the person who buys it pays the price and gets the counterfeit article, which of course then has to be, if they're suspicious, has to be examined by an artifact examiner and testified as to whether it is real or not, whether they've got the real thing. But as you all know, the whole of Southeast Asia, and this is not to cast aspersions at anyone in particular, but there are a lot of counterfeit goods, whether it's watches or whether it's iPhones or look-alike iPhones, Shanzai phones and so on, all kinds of devices that are made and wrapped to look exactly like the actual article. It's true of designer goods as well, I'm told, and so on. And you're very likely, particularly if you're like me, a foreigner and working or travelling in China, mainland China and Hong Kong, to be deceived, and if you buy something there, to be sold something which isn't the real McCoy, but a counterfeit or fake article. And the online auction fraud is the online extension of this kind of activity. So to do this, of course, you need to implement your Bayesian network. You need your conditional probability table, and the way that they got these was from a panel of experienced digital forensic experts within the Customs and Excise group at or department in Hong Kong government. This is, in other words, Michael Kwan's group, and they gave them a questionnaire, essentially, asking, what in your estimation would be the probability of finding this evidence if this particular action were carried out, and so on. So, in other words, trying to get the correct conditional probability, and then having a look at these and taking something like an average value of the scores of the experienced and or experts, maybe removing outliers and being a little bit careful in the way that they're performed. We're also careful to, having got some of these things, to see how sensitive they were, or the posterior output of the Bayesian network was. So performing various kinds of sensitivity analysis, the kind of manual one and the kind of one where you differentiate and so on, were done to just see how And indeed, what was really interesting to us was that the the posterior output of the Bayesian network's not particularly sensitive at all, plus or minus 10% maximum, with variations right across the range of the CPT values that the experts produced for us. So going right to the extreme ends of min and max, which was encouraging at least, and in some sense, in an informal way, kind of validated, I guess, the values that we ended up with to use. Now, you probably can't read this, but this is I suppose I could say, Bayesian network for the prosecution. And when we come to it, just to give you a step ahead, you'll see that the Bayesian network for the defence is identical in the sense that it has exactly the same evidences, because the evidence isn't contested, and the architecture, if you like, the structure is the same. In other words, 3 sub-hypotheses coming from the root hypothesis, just 3 different ones, which means that they can be compared. So the root hypothesis prosecution is the seized computer has been used as a transaction tool for the auction of a fake item. Now, that's divided into sort of 3 sub-hypotheses, that the uploading of auction material, that's not to say the item itself, but the description of the item, the cost and the provenance and all that material related to the fake item has been performed, so they'll be looking for evidence for that, and that's what the evidences E1 up to E5 are doing over there on the left, so we'll come to them in a minute. Then the second stage or step that they identify is that there has been a manipulation of the corresponding auction item has taken place. That's to say, not the item itself, they should have said the data, the information about the auction item has taken place. In other words, to make it appear as genuine as possible and so on. And then there has finally been some communication, either via instant messaging or email, between the seller and the buyer of the fake item, and they'll be looking for that evidence as well. And for each of these sub-hypotheses then, they have some bits of items of digital evidence, some artifacts that they would be looking for. And just to give you a feel, we won't read right through them, but to give you a feel for what digital evidence looks like as opposed to, as it were, glass or DNA or fingerprints and other more physical things. I've indicated some already, but the first one says, for example, material about the auctioned fake item, for example, an image file, text files describing it was found on the seized computer. That's to say, this is the computer of the person who was trying to sell the item, who's put it up on the auction site. The seller's account login record was retrieved from the auction site. In other words, they need to get access not only to the computer owned by the supposed seller, but also they need to get access to the auction site itself to see who logged in and when and so on. Then metadata of the file found on the seized computer matched, this doesn't mean matched in the way that we were talking earlier, with that found at the auction site. That's to say that the upload of the files from the seller's PC, let's say, to the auction site, the time, the date, and so on, agree, and so on and so forth. The IP address, Internet Protocol address assigned to the seized computer matched with that which performed the data transfer, again, which you can see from the website. And the Internet history, if they hadn't been deleted, the browser cache, the cookie file maybe, and the history file, and so on, will contain the contents for transferring the auctioned item material found on the seized computer. In other words, there was evidence of each of the digital evidence of each of the things which that hypothesis H1 asserts happened. And then similarly, there'll be items of evidence for H2 here. Again, in a similar way, and again looking for on the seller's computer, which was seized, looking for evidence of these messages, instant messages or emails, conversing with, having a conversation with with the buyer of. So this is a typical prosecution Bayesian network model for the prosecution side of it, of the of the case. Defence side looks remarkably similar. It's called everything's P instead of D, but notice please at the beginning, I don't know why they did this, but HD isn't what you'd think. It's exactly the same as HP. The computer has been used as a transaction tool for auctioning the fake items. So that means that we're going to use not HD when we actually come to do a likelihood ratio, of course, because they've made HD the same as HP for reasons I'm not privy to, I'm afraid. But so what they've got here is, again, three sub-hypotheses. The auction material related to the fake item was downloaded from the auction site. This time, the non-fake or non-fake auction item details or data was manipulated. The defence claim, probably of an item which appeared the same, but is actually the real McCoy, not the counterfeit one. You see. And then again, communication between the seller and buyer on non-fake auction items occurred, because there's no way of telling necessarily in the communication whether you're talking about a fake or a genuine item. So then you've got all the evidence absolutely as before. Okay, so everything from ED1 to ED13 are identical, and then because okay, I should say, where does this come from? This is because, as I said, this is one of the 5 or 6 most common digital crimes in Hong Kong. So they get a lot of these cases, so they know what the defence will be. They get used to the defence, and so the defence, they've basically codified into this Bayesian network in terms of the 3 sub-hypotheses, what the defence claims happened, as opposed to what the prosecution claims. So that's where that Bayesian network comes from, is what the defence codifies what the defence uses as the defence when they plead not guilty. And so you get a likelihood ratio, and in this case, because these are the 2 naive Bayes networks, then we can just product, everything's independent, and we just product everything up, and using the kind of these median values for the CPT values and so on, we get a big number with a plus or minus 10% error bar, which is, strongly or whatever. But this is the sort of thing that the prosecutors and the forensic investigators feel they need to know in order to feel that they've definitely got a case which is likely to succeed before they actually go as far as taking it to court. So this number will not go to the magistrate or the judge or the jury necessarily. In fact, I don't think these numbers have ever propagated into the courtroom itself, although there is some talk that in the not too distant future these numbers may well be, or numbers like this kind of number, may be sort of used and accepted as evidence, which is a little bit different perhaps to what's happened in the UK, where we have regressed somewhat, as some of you will know who've read Norman and Martin's recent report on things after R versus T and all the rest of it, where we feel a lot less confident about being accepted to produce numbers. But here these numbers are something which they, in terms of the forensic services, the digital forensic services, the police, prosecuting authorities find useful. I'm just realising.
You said these 30 things are independent, but your model says they're not independent. It says they belong together in groups, and within each group there is dependence.
Let me just go back.
HD1, HD2, HD3, those nodes create dependence between some subgroups of E's.
Oh, perhaps they do. Let me think.
Maybe
Well,
yeah, it's conditional, isn't it?
Yeah,
it's conditional independence. I think yes. There's no necessarily no time separating, no time dependence in this, but we can. Yes, I think it's probably more correct to say that they're conditionally independent rather than independent. I'm conscious I'm running out of time, so shall I just whip through the last 3 or so slides, and then we could. So the other thing that they're particularly interested in is probative value, or probative weight, as I think the Americans like to call it. So this is an individual piece of evidence, of digital evidence, they want to know whether this piece of evidence is really crucial to a case or not, because there's two reasons for this. One is, if it's not crucial to the case, maybe if everything else is there, you don't have to go looking for it, even if it exists. And if it does exist and you go looking for it, it might be very expensive to find. For example, not very long ago, the Metropolitan Police contacted me and said, has King's College got a scanning electron microscope? Because we want to look at a latch on an SSD memory of a phone related to a terrorist case, and we need to know whether this gate is charged or not, because we may destroy everything that's in the SSD memory, whether it's latching if it's charged, and we try and access it. So this is expensive, this kind of thing. I mean, well, relatively, £90 an hour apparently for a SEM at King's, so you know there are costs associated. So we've run the Bayesian network twice for particular trace evidence. Well, once with all the evidence there, and then once with, let's say, evidence trace EI removed. In other words, just not available, not found. And then the difference in the posterior outputs of the Bayesian network between when everything's there and when what a particular evidence is missing is a measure of, I don't mean a numeric quantitative measure, but a ranking measure of the probative value of that particular EI, that particular evidence. And the case study that we've got is elicits, in Hong Kong again, peer-to-peer uploading of copyright protected material with BitTorrent. Now, again, Hong Kong, as you know, used to be a British colony until 1995 or something. 6? Yeah. And then, so their laws are quite English or English-Welsh laws in general. But one thing that's a bit different is that in the UK, or at least in England and Wales, it's not only illegal to upload copyright-protected material, it's also illegal to download it. However, in Hong Kong, on these peer-to-peer networks, the law is framed in such a way, but it's only illegal to be the uploader, and in BitTorrent, the first seeder, as it would be called. And anybody who downloads from something that's been uploaded is not themselves committing a crime. It's only the person that puts it there, as it were. So we're only really interested in the uploading, not in the downloading. Again, the conditional probability table values were elicited from a panel of experienced DF experts, this time in the cyber group of the police, Frank Law's group. And again, we performed sensitivity analyses on these values to see how stable the outputs were compared to the, as we varied these right across the range of values that the experts gave us. And again, it was plus or minus 10%, so we've got some stability, which I think is an important thing to know. So that's the Bayesian network for the BitTorrent upload. Again, I don't probably need to talk you through the whole thing, but you can see this time there are 5 sub-hypotheses, and there are 3 bits of evidence associated with the first one, then 5 associated with the second. There's a shared one. In fact, there's one that's shared amongst 3 sub-hypotheses. E13 shared amongst 3, that's right, and E8 and E4, yes, are shared amongst 2. So slightly more complex Bayesian network, and again, all the evidential traces that will be looked for are listed there, but you know, it's kind of fairly standard stuff for computer science people, and I won't spend a lot of time going through that, given that time is short. So what we did then was to rank those differences between the posterior output of the Bayesian net when everything's there, with the posterior output of the Bayesian net when one item of evidence is removed, and we'll find that the biggest difference is E18, then when E13 is removed, then when E3, then E1, and E1 and E2 turn out to be about the same, and after that, so very, very small numbers. And if we just check back what those are, then you just double check. E18, all right, so E18 is the internet history record about the tracker server connection is found. In other words, that proves pretty much beyond a doubt that there is an internet history record for the server that serves that tracks the BitTorrent upload. That we found the evidence for that Then the next one, as you'll see, was E13, which says, well, not surprisingly, an internet connection is available. Well, yes, you would rather hope it was, because without it, sine qua non, I think.
That's informative, isn't it?
Yeah, well, is it? Yes.
It doesn't cost too much to check that out.
These days, particularly, and so on. So one could then start to imagine producing, and this is where I come back to what I said at the very beginning about volume and variety. This takes us to triage and the problems of having to scan and screen and filter enormous numbers of devices, enormous quantities of data. How to go about devising triage schema. So in this particular case, it looks like we should go for the big wins, the lower hanging fruit, if you like, first. We should look for E18 first, and then E13, and so on, down the line. Because it might be that if you didn't find E18, you might think, gosh, well, that's the biggest one. Then maybe the case isn't going to be strong enough anyway, because that evidence is not there, given everything else, of course. So this led to the idea of a cost-effective triage scheme, which I've more or less just suggested. So once measures of probative value are known, you could devise a cost-effective triage scheme where you rank what we've just done here, the expected evidential traces EI in decreasing order of probative weight, and then sub-rank anything. You saw we had E1 and E2 equal, and they were exactly equal for genuine reasons. Sub-rank them in increasing order of cost-benefit ratio. In other words, you might have that E1 and E2 both had the same probative value, but E2 was much, much more expensive to recover, because it needed a scanning tunneling electron microscope to go and examine a latch on a SSD memory, whereas the other one was quite straightforward with a software tool. So sub-rank them in terms of cost of their increasing order of cost-benefit ratio, so that we would take the investigator time plus the equipment costs needed and divide by the probative value to get a rough measure of cost-benefit ratio for that particular piece of evidence. And then you recover traces of evidential traces of high probative value will be recovered early on. Missing high probative value traces might cause investigation to be deprioritized, or even, bad really case, abandoned. Traces of low probative value will be covered later on, if at all, because low probative value traces with a very high cost-benefit ratio might be excluded from the investigation on the grounds that it simply wasn't cost-effective and you've got enough probative value there already. So, to summarise, the application of Bayesian networks to investigation of commonly occurring digital crimes in Hong Kong has permitted us to, first of all, I think, help investigators and prosecution defence officials to obtain a quantitative measure of the plausibility of their and their opponent's case. In other words, it's a bit like a game of chess. I can see what you've got and you can see what pieces I've got, so we can modify our tactics in an adversarial legal system accordingly. And we can and one side can then anticipate what the other side's move will be and get ready a countermeasure for that, and so on. And secondly, investigators can adopt a cost-effective triage scheme which aims to recover what I call low-hanging fruit early on and allows for deprioritisation if appropriate. And I think that's it. Yes, sorry to overrun.
I guess we just have time for maybe 2 or 3 small questions. I kind of was just making a comment myself first. You mentioned Cliff Stoll at the beginning of your talk as kind of the father, and I encountered him recently. He's reinvented himself as a glass blower of Klein bottles.
Oh, wow.
Which you can easily find on the web. Acme Klein. I ordered a glass Klein bottle.
Wow.
And then I learned about this incredible history that he had.
Yeah, no, it's amazing. I mean, I've got the cuckoo's egg and all the other stuff that he wrote. It's brilliant
Cliff
stuff.
Stoll by getting yourself a Klein bottle. Dave?
Yeah, I'm just interested in, you use probative value, you just use a difference measure. You're not going back from the ultimate posterior taking.
Yeah.
So did you explore different methods of
Not yet. It's quite recent. We've only done this in the last month or so. So we're still thinking about whether there might be better ways. And if you've got some better suggestions,
at
please.
least 5 other measures,
Right.
but they all have different properties, which I don't exactly understand.
Okay.
But I can definitely.
That'd be great. I'd be really glad of that.
Yeah, different log versions of the.
Okay, that sounds fantastic. Thank you, Dave. Yeah, that'd be great. There's something there.
I'm totally ignorant of Bayesian networks, but one question that came to my mind is, as a physicist, maybe as a former physicist, what's the interaction between the independence hypothesis and the topology of the network? In other words, your network was just a tree,
Yep.
and you said things were quote independent. I'm not sure what it means. And then the outcome was you just take the product of the probabilities. So how do you create loops, or why do you create loops, and what's the interaction on the connection between independence and the topology, or the non-existence of the topology, which is being a tree?
Yeah. Okay. So yes. So all Bayesian networks are trees, effectively.
Oh, they're only trees, and no loops at all.
No.
No.
Many Bayesian networks are trees.
Okay. All the Bayesian networks I've ever come across.
Yours
wasn't a tree.
Sorry?
Your second one wasn't a tree because you had the common.
Yeah, right. Sorry. Yes, you're absolutely right. Yes, sorry. Yeah, the second one wasn't a tree. You're absolutely right. Sorry. Yeah, you're absolutely right. Yeah. In fact, there was a move. The Hong Kong group were quite worried about actually having those crosslinks, which cause it to become cyclic rather than acyclic.
But direct is cyclic.
Yeah.
Direct,
So-
that is, there's
well,
no
it's direct-
actual
yeah.
cycle. If you follow the arrows, that's what you really need.
Yeah, that's exactly right.
So your tree is, your
Yeah.
graph is fine.
Yeah, so the graphs are right, but the arrows all go one way at least. They don't go back up.
Yeah.
Effectiveness for that.
Yeah, but again, what's
Yeah.
the feedback? I mean, what's the idea of the network in the sense that what's the independence assumption has to do? What does the independence assumption have to do with the topology, if anything? Or what is independent exactly?
Well, okay, if
Or is there any
Yeah, well,
feedback that you
okay.
can see from the network?
so, if probabilities are independent, we hope to be able to multiply them together. Okay,
Sure.
so
I think I
so
have a feeling so really why
one
you
aspect.
answered this question,
Yeah.
right?
I want to go.
So
Both Professor Gill gave it, and this gentleman mentioned the independence assumption. It's actually crucial. Take your second example.
yeah,
E13 was having an internet connection. That clearly has to be dependent. The other things
Everything will depend on that.
has to depend on it.
Everything else will
So
depend.
therefore, multiplication it exaggerates the strength of the evidence.
yes,
I mean,
yeah,
if you go back many years ago, even classical robust methods are very sensitive to dependence. So probably, I mean, you still will probably get a very high LR, but it won't be 200,000.
yeah.
In other words, if
yeah.
you incorporate the dependencies. But in the second graph, it's clear that E13 depends on everything.
There's a follow-up to that, or an interesting sort of what's the word I want? Correlation to that, not correlation. That a colleague suggested to me only a few weeks ago that actually, when you have something like an internet connection was available, that this, because it's a kind of sine qua non, without which you can't actually have the claim. This should be actually considered as anti-evidence. In other words, it should be something without. If you don't have that, you don't even go into the other thing and go into the
That's probably true, isn't it?
prioritisation.
If you don't have that, you don't even do the investigation.
Well, that's right. So in other words, what you should do is you should look for these pieces of so-called anti-evidence first, and make sure they are actually fulfilled or not fulfilled, depending on which way round you phrase it. And then don't even go into the investigation if the thing isn't there. So you have a prior stage, a kind of pre-processing stage, where you filter out any of these things which just have to be there.
I have to stop you and move on to the next speaker, because we're a little over time.
Oh, sorry.
Thanks, guys.